Hello, welcome to skill 4.2, which is one of my favorite skills, applications of exponential functions. And trust me, you're going to need to know what an exponential function is because a lot of you will be thinking about things like retirement accounts or interest rates. And at the heart of it, a lot of those are dictated by exponential functions. And I'm going to start here with a little graphic. And this is looking at saving at 25 versus saving with 35. And let's say that you retire when you're 65. What you can kind of see here is that there's over $100,000 difference, or almost $100,000 difference with the same type of savings behavior just by starting like 10 years earlier. So it really adds up over time. So let's get started with an example of a retirement account. So let's say that you come into a job, maybe you saved $26,000 and your company offers you a 401k, which is a special type of retirement account with a guaranteed growth rate of 6%. And by the way, what you will notice in our formulas is that R is in decimal form. So that's going to be 0.06. So to qualify, you must first deposit $26,000 into your retirement account by the end of the year, assuming that you do not put any more money into your retirement account. How much will you have saved after you retire in 40 years? So we're just going to start at year one. You know, we come in with a $26,000 balance in our account. So maybe you've had a job that you saved $26,000. And you're going to do 26,000 times 0.06. And we want to know how much interest we earn in that first year. So we actually earn $15.60. And then we're just going to add the 26,000 and the 15.60. And we're going to be at 27,560. So essentially just having your money sit there, you're earning over $1,000 even with like a $26,000 balance. Now, by the time you retire, ideally you should be actually, reaching somewhere into seven figures if you are playing it right. So then we're going to take that 27,560 and kind of subject it to the interest rate again. And when I do that, I'm going to do 27,560 times 0.06. And because we have like a higher starting balance, we're actually going to get even more interest. So we're going to get 16,5360. And then if we just add those columns, we get 27,560 plus, and you want to have a good calculator with you, 16,5360. So we're at 29,213.60. And then we put that in for the third year. So I have 29,213.60. And I'm going to multiply that by 0.06. And we're going to get even more interest. So when we do that, we're going to do times 0.06. So we're going to get 1752 and 82 cents, give or take. And we add that to the 29,213.60. And we are at 30,966.42. And this creates kind of a general formula here. So we don't want to do this like 40 times, but we can kind of say that our general formula is equal to A times 1 plus R to the T. Where A is the initial amount. R is interest rate or percent rate in decimal form. And then T is time. And just by having this formula, we can actually, instead of like having to do this thing 40 times, we can just put this right into a formula and we can figure out how much is in our retirement account. So I'm going to do 26,000 times 1.06 to the 40th power. So you want to find the exponent key on your calculator, and even with your smartphone here, I'll tell you what, I mean, I've told my students all the time, you know, be careful with Mr. Benzel and a calculator. I've had salesmen actually yell at me before when I've taken my calculator because I know their games. And I could do like 1.06, and there's an exponent key even on like an iPhone. It's the X to the Y, or you could use your Delta Math calculator to the 40th. And then you're just going to multiply by 26,000. And you end up with $267,000 and 429. Yeah, 267, 429 about. So just all that from just having your money sit there in a retirement account and not being used. We also have population growth here. Basic population growth problems, you know, kind of have the same formula. So that formula is going to be 864 for our initial amount. The starting year we call T equals 0. And then the growth rate is just going to be for your R, that's going to be 0.017. And it says, assuming the rate will be constant, what is the population of Indianapolis going to be in the year 2030? So we will say that the population is going to be 864, which is our A times 1 plus R to the T. So 1 plus R is going to be 1.017. And the T is going to be, let's see, 2030 means that your T is equal to, it's 11 years after 2019. So we're going to do 11. And then we're just going to enter that into our calculator. So I got 1.017 to the 11th power. And that's going to be 1.017 203 times 864. So we're at 1,040.0 thousand, which is really the equivalent of like in the million. So it's like 1,040,000. But I like kind of just putting like the smaller, truncated numbers in there. And we could kind of just come up with a general equation. So I could do 864 times 1.017 to the t. And I can actually literally play around with it as well. So I'm just going to kind of show you how to enter that in Delta Math before we go to the next example. So there's a convenient calculator icon on the top left right corner of your Delta Math. And you can kind of put the like 864 times 1.017. And there's a exponent key, so a to the b. And you can put however many number of years later. So let's say I want to see after 50 years, for instance, I would actually be in the 2 millions in that case. And I could just kind of play around with my numbers here and change like the number of years. All right, we also have the opposite of exponential growth. We have exponential decay. So what we can say about this is that the formula instead for decay is going to be 1 minus r and make sure that you have the initial amount to the t. And let's say that we want to buy the car depreciates in value. So 1 minus r is 1 minus 0.099. And that's going to be 0.901. So we can actually just come up with a general equation here. So this is going to be 36,000 times 0.901 to the t. So when I plug it in, you may just want to show like one plugin, for instance. So like, let's say I want to do it after, now I'm just going to put kind of a general formula here, 36,000 times 0.901 to the t. So you want to do, like if I want to do after 1 year, I could just do 36,000 times 0.901. And after that first year, I'm down to 32,436. And then I multiply by 0.901 again. And again. So if I do 32,436 times 0.901, I'm down to 29,224. And then if I do 0.901 again, I'm down to 26,331. And then if I have, like, let's say after 5 years, I could just do, 36,000 times 0.901 to the fifth. And if I just enter that into my calculator, whether it be, my cell phone calculator or Delta Math, if you have an iPhone, if you want the exponent key, just put your iPhone to the side. So I have that times 36,000. I like to do the exponents first, kind of in the spirit of order of operations. And I'm actually down to 21,376. So the car is like practically half its value. All right, so we're gonna go from finances to sciences here. So not only do we need exponential functions to understand things like what it means to take out a loan or a savings account, but we also need to kind of, if you want to do like biology seriously or something like that, or chemistry, you have to have a good command of exponential functions. So we have a half-life formula. So I would suggest when you have a formula of something you haven't seen before on Delta Math, that you actually spend the time and take a look at the solution and look at the general formula and think about what each letter stands for. So the first letter here is A, so that's initial amount. The T is time. So we want to know how much of the element is left after 13 hours. So we could say that T is equal to 13. 2,200 is our A, because that's our initial amount. So the good news is if you have a good read of the problem, you can actually figure out what all the variables are. And even though these formulas look big and bad, you can let the calculator take care of the rest. And then the H is going to be double every 6 hours. So I should say that there is a double formula as well. And that would be Y equals to A times 2 to the T over H, or like the double life instead. And then H would be the time to double or half. And this problem is kind of the opposite of half-life, so we're actually doubling, but it's the same exact idea. The only difference is that you're going to have the double formula instead. So we're going to put our initial amount. So we have 2,200 times 2 to the 13 over 6. And now you just kind of let the calculator take care of it. So you could go to your Delta Math calculator. I suggest that if you have a fractional exponent, that you spend the time putting parentheses around your fractional exponent. So and when we enter this in our calculator, it says how much is there going to be after 13 hours. So it actually kind of quadruples itself. So we're at 98, 77, 66. So if you ever work in like pathology or biology, these type of equations, You can actually look at things like how bacteria grows or how cancer grows or stuff like that. Another thing that we're going to see is compound interest. So please make sure that you copy these formulas down. P means principal. So when you take out a mortgage or a loan, principal, which is P, this just means initial amount. So if you take out a mortgage, for instance, like let's say you buy a house and you take out a mortgage for 150,000, that would be your principal. Or if you buy a car and you take out a $20,000 loan, that would be your principal. Interest rate is interest rate no matter how you cut it. So always put your R in decimal form. N is the number of times that the interest is applied in the period. So if we are doing compounded monthly, for instance, we would have 12 times in the period of a year. If I had weekly, it would be like 52 instead, for like 52 weeks in the year. And then T would just be like the number of time periods. So there'll be a few of these compounded ones on Delta Math to kind of give you a little bit of practice. So thank you for tuning in on here. And I hope that you are using your formulas and then thinking about what each letter stands for. So in summary, growth, you add the interest rate or add the percentage rate. Decay, you subtract the percentage rate. Always put percentages into decimal form and know what each variable or letter stands for. And if you do these things, you could just put these in your calculator and you'd be surprised what you could discover.